Did Beth just leave?
Yeah, I think does she go today?
No.
She's
Okay. Yeah, probably if they just got there, they just don't have the internet yet.
Can everyone see
Um,
this?
yeah, I can.
Okay. All right, I guess I shall start. So, my paper, it was called Thalidomide Conjugation as a Strategy for In Vivo Target Protein Degradation. So, thalidomides, they are basically a class of drugs that were introduced in the 1950s, and they initially started off as a sedative, and then they used it as an anti-nausea medication in pregnant women. But then what they realized was that it was a teratogen. So that's basically describes an agent that can disturb the development of the embryo or the fetus, and it can cause birth defects, and it was causing birth defects. So that's the most common thalidomide is thalidomide. And I watched a video on it, and they were basically saying that they were using two different conformations of the thalidomide. So what they were seeing was that when it was in the R configuration, that it was alleviating nausea, but then when it was in the S configuration, that's what was causing the birth defects. But then they eventually just banned it in general, just because it's not safe for pregnant women. However, it's being used to treat certain cancers, such as erythromyonodiosum leprosium, multiple myeloma, and myelodysplasia. So essentially in this paper, what happened was they did ligand affinity chromatography, and they discovered this component of a colon ring ubiquitin ligase, and that's called CRBN. And what they realized is that the thalidomide could bind to the CRBN, and this was pretty pivotal for people who kind of understood what a PROTAC could do, because if you have an E3 ligase and you have something that binds to it, you can find other molecules that will also bind, and then you can degrade a protein. I'm not sure if it's of your choice, but you probably have a pretty wide selection of different proteins that you would like to degrade. So here's the breakdown of the components that were in the paper. So you have the target protein, which is the BRD4, and this is a typical target protein because the inactivation of BRD4 on the chromatin can actually lead to illicit transcriptional downregulation of an oncogene gene, and it produces an anti-proliferative response or an inhibition of cell growth. So that's why the turning off of this, protein is really beneficial in anti-cancer therapy. So they use that as the target protein. Then they have a molecule or compound that they created themselves. It's called JQ1, and it's a direct acting inhibitor for the BRD4 protein. So what they did was they basically figured out a way to bind this protein to the BRD4. Then you have the thalidomide, which we just talked about, and that's able to bind to the CRBN or the E3 ligase. Then you have the CRBN, which is the E3 ligase, and then DBET1. They just used that term to just describe the whole PROTAC in general. So DBET1 would be the JQ1, a linker, and then thalidomide. So here are some structures of kind of what we're looking at. So first we have JQ1 and the S conformation, which will be important later. And then you have the structure of thalidomide. And like I said, thalidomides are a class of drugs, so there are different types of them. So this over here, it's basically showing you, what could change on this structure that would make it one of these three molecules. So because this is a carbonyl group here, that's what makes it thalidomide. And then down here, you can see the structure of the DBET1. And that is the whole PROTAC, which is the JQ1 and the S conformation. Then you have a linker, and then you have the thalidomide over here. Then down here, I didn't make these, but they were in the paper, and it's basically a 3D visualization of, you know, this is describing just the PROTAC, so just DBET1. But then over here, you have the entire PROTAC scheme. So at the very top, this part, this is a CRBN. Then you have the yellow and like this yellow mass here, that's the DBET1. And then the ribbons are the BRD4. So now they kind
That's
of
the
realize.
whole thing. I'm sorry, Naya, but that picture is just crazy. That is it right there, right? The PROTAC holding the target protein next to the E3 ligase from the two halves of the PROTAC. Like that's an amazing structure.
Yes.
All right.
So now that they know that they can, you know, successfully bind everything together, they wanted to first prove that, and then also kind of measure different variables that might interfere with the binding. And how they did this was by using a technique called alpha screening. So essentially with this, you have two different beads, and they can illuminate. And what happens is when the beads are closer together, they have high luminescence, and when they are farther apart, they show low luminescence. And this is pretty useful when you think about what a PROTAC does in general, how like the foundation of a PROTAC is being able to successfully bind things together, basically. And you know, to have a technology that can measure proximity and binding, it's pretty, you know, beneficial for using PROTACs. So in this first assay, you start off with, they have the beads, they're doing alpha screening, and you start with the beads pretty close together, and that, you know, produces high luminescence. And Scott and I were kind of like on the fence about what, I didn't know if there was a PROTAC involved in here. Scott, I think thinks there's a PROTAC in between these two, right? Or do you think it's just the beads?
I think this first one is not the PROTAC. I think in this first one, what is holding the two beads together is on one bead there is BRD4, and on the other bead there is JQ1.
Okay.
Yeah. They use, I think they do, as you see, they do use the PROTAC to see if they can make the beads dissociate. But I don't think there's a PROTAC in the beginning.
Okay.
Yeah. It was confusing though, Naya, because they actually really did not do a very good job of explaining the situation of what was on the beads. I think they did a little bit better with the second alpha.
One's a little bit more straightforward.
I think so. Yeah. Okay.
Okay. So, and you know, PROTAC or not, I think like just the understanding of what I'll describe what this assay is really looking at, and kind of just getting to familiar with analyzing alpha screening. So what they did was they started off with the two beads, one coated with BRD4, the other one with JQ1. And then what this graph is showing, so to this side and the y-axis, you can see it's kind of a percentage of the luminescence. And then on the y, it's the amount of the concentration of the compounds they added. So you can see over here, this is the, these are the compounds they added. And then this is just what we talked about yesterday, how it's like the half maximal like measurement or concentration of some sort of compound that will inhibit the function of something else. So that's what that's showing. So basically what happens is over here, they add the DBET1, And you can see that the DBET1 cause the beads to dissociate and move farther apart from one another, kind of breaking the binding. Then you can also see that in JQ1, where the addition of free JQ1 also disrupted the binding, causing the beads to move farther apart and for there to be lower luminescence. And that's kind of, visualized here. And you can see that also it was a pretty low concentration of these two that caused them to dissociate. And then if you look at the DBET1 in the R conformation and the JQ1 in the R conformation, those did not cause the beads to dissociate that far from each other, because you can still see there's a very high luminescence. And that's why I kind of said that in the beginning, the JQ1, that the fact that it was in the S conformation was very important, because when it's not in the S conformation and it's in the R conformation, it does not cause any breakage of binding. So that's pretty important to know.
Do you all sort of understand, the rest of everybody, do you kind of understand this assay? Because it's not easy to see what's happening. And somebody else actually has some alpha screen experiments. I think it's Beth, who is, I think, only partly with us. Oh, there she is. Hi, Beth. I've been thinking about this a lot, Naya, because Naya and I talked about it. This is my analogy. Are you ready?
Mm-hmm.
So BRD4 and JQ1 bind each other. They kind of know that already. Mm-hmm. And so imagine that's like a hand and like a baseball glove, right? So then if they put the baseball glove on one bead and the hand on the other bead, then they can get the beads to bind each other, right? Mm-hmm. Then they're asking, what things can I add to this complex to make it come apart, right? So if JQ1 is the little molecule, that's like the hand, and then the BRD4 is like the glove. What they're showing is that if they like take a bunch of mannequin hands and just start like adding them, the mannequin hands will take the place in the glove, and then the bead will come off. Do you understand what I'm saying? But then, of course, it has to be the right hand, right? Because baseball gloves are like, if you're right-handed, it goes on your left hand, right? So only left-handed mannequin hands would work. And that's what they're showing with the JQ1 that's the R, that you can't add the wrong mannequin hand. It doesn't work anymore. So they're trying to like compete off the interaction, which is but the weird thing, like we talked about, is like they didn't totally explicitly say in this case what was on the beads. I still don't understand, but I think it has to be kind of like that.
Yeah.
Okay.
Okay. So then in this assay, it's kind of the same concept. So what they did was they started with the beads together, but this time the beads were coated with BRD4 and the CRBN, and they contain the PROTAC in the middle. And what this is kind of measuring is what different components that they added that cause either high luminescence or low luminescence. And so for this column, it has DMSO, and that's basically like the solvent that all of these compounds are in. So you can consider that a control. Then what you see here is that when they added the free JQ1 in the S conformation, it produced low luminescence with the beads. So basically what happened is the free JQ1 kind of washed off the JQ1 that's attached to the PROTAC. So there's no way for it to bind anymore. So that's why it's showing low luminescence, because the beads are either farther apart from each other, or there's no binding, which is what alpha screening measures. And then when they added an enantiomer of the thalidomide, which I kind of talked about prior when they were looking at the different like conformations of thalidomide, that also produced low luminescence. So I'm assuming what also happened is that the free thalidomide washed off the thalidomide of the PROTAC. So yeah, as Scott said, basically they wanted to see what was outcompeting, you know, what addition of something is going to outcompete the whatever's on the PROTAC, whatever's like forming those bonds. And then you can see that the JQ1 and the R conformation did not cause the beads to dissociate from one another. And the other enantiomer of the thalidomide also did not cause really much of any dissociation of the beads because they're still pretty high luminescence. And Scott actually made a good connection, and that it was kind of like Le Chatelier's principle, or like in the realm where, you know, you're adding too much of something, and so it disrupts the equilibrium, causing the lack of binding. And that is pretty much it.
All right. Do you have any questions for Naya?
I have one. So,
Go ahead.
Naya, that slide you have, I think it's up a couple slides where you like identify what the different shapes are.
Yes.
Not that one. One above it, I think.
Okay.
That one. So I remember you've like used this for different, like I think they were different pounds before. Are these just like models, and what you're assigning them to is different? Like they always have this general setup, like the blue binds to the red and the yellow to the purple. And
Yeah,
then
that's kind of what I was getting at, because I was like, okay, like if they're familiar with this kind of figure, and it's essentially the same thing. Like PROTACs are basically like, there's no, I guess, like change in them. They basically do the exact same, or supposed to do the exact same thing every time, and they're going to be set up the same way, basically, with whatever, you know, the varying different compounds that you can use. That's what I've kind of gathered from this.
Right. So that is that whole like red, blue, linker, yellow, purple, is that whole thing the PROTAC, or just the linker between them?
Just the JQ1, which is the blue, then the linker, and the thalidomide. These other, this is the target protein, the E3 ligase. So yeah, this is just the whole PROTAC right
So
here.
the yellow, the line, and the blue.
Mm-hmm.
Okay, cool.
So actually, can you go to slide 5? So if you look at so do the same analysis with E, Naya, for
Okay.
her. Yeah.
So just describe what these parts are, like what.
Yes.
Okay.
Please.
So this top part is essentially the purple, which is the E3 ligase, or the CRBN. And then this part here is the whole PROTAC. So then you would have, over here would be the thalidomide. Then in the middle, there's some sort of linker. And then down here would be the JQ1. And
Okay.
this whole thing is considered DBET1. That's what they called it. And then over here, the ribbon, it's attached to the BRD4. So this would be the target, and then, you know.
Okay. So when it
would
was
attach.
linked, it's DBET1.
Yeah, that's just what they called it.
Okay.
This is also, I mean, there, I guess before even like PROTACs got sort of invented, there was like an older, I guess, technology sort of, where that also, I just think it might be helpful to hear the name, that people used to make these molecules that had, just like a PROTAC, half of the molecule binds to one protein, and then they have a linker, and then there's another half of the molecule that binds another protein. And the name for those that are, they're not PROTACs, but they used to be called chemical inducers of dimerization, meaning that the molecule has two parts. One part binds one protein, the other part binds another protein, so it can induce two proteins to be close. And so you can perturb like a cell by artificially making two proteins be close. You know what I mean?
Mm-hmm.
PROTACs are a specific kind of chemical inducer of dimerization where you're bringing an enzyme that tags, like Naya said, right? That tags, that can able to add ubiquitin to the other protein, and then that causes that protein to be degraded and like absent from the cell.
Mhm.
So it's like a function, it's like a degrading chemical inducer of dimerization. Um, any other questions?
Okay, thank you.
And I would say just one thing that is one of the big things about this paper is, if you remember in Naya's other paper, the molecule that bound to the E3 ligase was the IPP peptide, which was like a really big molecule, like a really, really big molecule. One of the big advances here is that they replaced that with thalidomide, which only has a molecular weight of like 200 maybe, right? So it's starting to look more like a drug, right? That the E3 ligase binding half isn't this whopping thing anymore. It's now a small thing. That's what made people freak out.
Mhm.
Part. Yeah. Great. Thank you, Naya.